Now this slide shows you a crystalline material and an amorphous material. So can somebody define for me what a crystalline material is? How do you define a crystal? How do you know whether this is a crystal or not? That's the key word. So the atoms are arranged in a repeating manner so that you know that if you find a particular atom at this point, you'll also find it at this point, and this point. So we have long-range order inside the crystal. And this is one example where we have green atoms and red atoms. If I know that there's a green atom here, there must necessarily be another green atom here, and you carry on for a very long distance. Okay? So they are defined by the long-range periodicity of the atoms in the structure. Amorphous material, the atoms are arranged more or less at random. Okay? So there may be short-range order. That means, one of these red atoms is surrounded by 3 blue atoms, but you cannot predict where the next atom is going to lie or what kind of atom there will be. Can you give me an example of an amorphous material? Glass. What kind of glass? Sorry? I can't hear you. SiO2. Silica glass. Give me 2 more examples of glass. Quartz is silica. Actually, quartz can be crystalline or amorphous, the amorphous form. Yeah, but 2 other material kinds. Yes, polymers can be glassy, if they are below the glass transition temperature, and ceramics can be glassy. So give me one more. No, gas is not a glass. Yeah, it's not solid. Metals. Yeah, so you can get metallic glass as well, right? You simply need to cool fast enough so that there is no crystallization of the liquid. And some people say that metallic glass is liquid metal, but it's frozen, right? That isn't actually correct, because a liquid is able to relax at all temperatures. So as you cool it down, its density changes and other properties change. Whereas a glass is actually frozen into that state. So its properties change in a different way as you cool the temperature. Structure does not relax. So the difference between a crystal and an amorphous material is defined by the extent of order in the arrangement of atoms, long-range order. Okay? But liquids can also be crystals. Yeah? Can you give me an example of a product that you use every day which has liquid crystals in it? Yeah, liquid crystal displays. Yeah? So basically, the definition of a liquid is that it can't support a shear stress. Okay? That means it flows. So this is a liquid with, elongated molecules, and the molecules can slide past each other. Therefore, it's a liquid. But you can clearly see that there is some sort of order in this. Okay? Therefore, it's not a random arrangement of molecules. It's actually a liquid crystalline material. There are different kinds of liquid crystalline material that you can get, and it's the alignment of those molecules which helps you to make displays, because you pass light through it through an analyzer and a polarizer. And the analyzer and polarizer are crossed, so no light goes through that. When you apply an electrical field, the molecules align along one of those grids, and therefore allows light to go through. Okay? So liquid crystalline displays exploit the fact that it's a liquid, so the molecules can easily swing around if you apply an appropriate field. Whereas, of course, in solids, they can't do that. If you press the screen of your computer, you'll be able to see that the colors almost flow, and that's because there's liquid in there. Right. This is a very beautiful picture, and what most people would recognize as crystals. Yeah, if you ask the person in the street to comment on what is this, they would immediately think it is a crystal, and some people even say that crystals have magical properties of some sort. Yeah? But we are not at the moment going to cover that. The main point is that crystals are recognized by the fact that they have a beautiful shape. They may also have color and so forth. But we are interested in a more general form of crystal. So, for example, this is a single crystal, right? Do you recognize what this is? It's a turbine blade for an aircraft engine to work in the very high temperature region of the aircraft engine. And this part of it is a single crystal. Okay? It's made out of a nickel alloy. And what you do is you start solidification from here, and you're solidifying in a temperature gradient, so you get lots of crystals growing in this direction, and the one that is growing fastest fills up this spiral and blocks all the others. And therefore, the rest of it solidifies as a single crystal. Why do we need a single crystal for something that's operating at a very high temperature, something like 1400 degrees centigrade, and rotating extremely fast? Why do we need that? Sorry, louder please. Heat expansion will happen whether it's a single crystal or a polycrystal. Creep. Why does using a single crystal reduce creep? Yeah. So grain boundaries accelerate creep deformation. Why is that? What's wrong with grain? That's right. So the diffusion coefficient inside a boundary is higher than inside the volume of the material because the crystals don't match very well at interfaces. Okay? And you also pointed out that there could be some grain boundary sliding. So at high temperatures, grain boundaries weaken the material, but at low temperatures they strengthen the material because they provide obstacles to the propagation of slip between crystals. So here the crystal shape is an engineering shape. It's got an aerodynamic shape which provides thrust for the engine. Nothing to do with its internal crystalline symmetry. But you will see that the fact that this is a single crystal makes it anisotropic. That means its properties are different in different directions. You can see that very easily even if you look at the schematic diagram here, that the properties in this direction must be different from the properties in this direction because the spacing is different, the neighborhoods are different, and so on. And in the turbine blade, you actually grow the blade along a specific direction so that the elastic modulus is such that you reduce vibrations. You want as few vibrations inside an aircraft engine as possible. So you can exploit not only the fact that you don't have grain boundaries, but also that you can grow along directions which will minimize vibrations during the operation of the engine. Okay. So typically this might be rotating at 25,000 revolutions per minute inside an aircraft engine. So that's if you have vibrations, that's not a good thing. So this illustrates how the properties vary as a function of direction in a single crystal. So this surface, a vector from the center to this surface, represents the modulus. And a single crystal of silver, you can see that the modulus is not constant. It varies as a function of directions. There will be certain soft directions which, if you stress along soft directions, then the amplitude of vibrations will be large. If you stretch along a stiff direction, then the amplitude will be small. Okay? And this is in the case of a body-centered cubic metal, molybdenum, where again you see that the modulus is not identical. It's only when we put crystals together in random orientations that we can obtain isotropic properties. But there is no metal or crystal in which you can get isotropic properties by a single crystal. Okay, so the vast majority of engineering materials that we deal with are not single crystals, they are polycrystals. Here is a typical example of an optical micrograph which shows hundreds of crystals which are packed together in such a way that you fill the space. So there are no holes in this material. When the crystals grow, they're growing from different points, they will touch, and therefore they will fill all the space. And these are the boundaries between the crystals, the so-called grain boundary. So another name for a crystal is a grain, because it's like a grain of salt. Yeah? In fact, a grain of salt might itself be a single crystal. So we have these crystals, and in between them we have some grain boundaries. And crystallography is not just about single crystals. We need to look at how crystals of different kinds, when we put them together, they behave. Okay? So we will have grain boundaries, and the grain boundaries will not be identical. This boundary here, which is between this crystal and this crystal, will be different from this boundary here. And you can see that there are some special boundaries as well. So that actually is an annealing twin. And you can see that the shape of that boundary tends to be nice and straight because they are low energy interfaces which are much better fit between the two crystals than a boundary of this sort. Okay? So there's a lot of complexity in this, and we can engineer that complexity to get the best properties. And the properties need not be mechanical. They can be electrical properties, for example, or magnetic properties, and so on. Yeah, so can you give me an example of a material where we control the grain structure in order to obtain the best magnetic properties? Yeah? Silicon steel, in order to get least resistance to the movement of domains, right? Magnetic domains. These pictures are now very common. The micrograph that I showed you first gives you the shape of the crystals and the size of the crystals, but it doesn't tell you anything about the orientation of the crystal. Here, the colors represent different crystal orientations. So now you not only have the shape of the crystal, the size of the crystal, but also its crystallographic orientation. And this technique you can use on a scanning electron microscope or a transmission electron microscope, because you get diffraction information from all of the individual crystals, collect all that, and produce a map like this. And you should realize that this is a very nice looking map, but there is a huge amount of information locked away in that. When you do an EBSD, electron backscatter diffraction experiment, you are collecting a vast amount of data. And in 99% of the cases, you don't make use of that data. You just look at the picture, yeah, and present it. But in 99% of the cases, you do not do an analysis of the orientations of the crystals and how this boundary interacts with this boundary, and so on and so on. So you should spend at least a month on every picture looking at the detail, and then you will discover something new. Yeah? Of course, you may not have time to complete your PhD, but you will be excited by the information that you see. Okay, Now I'm going to introduce you to a concept which is completely imaginary. It doesn't exist, but we like to find patterns in data, and this is a way of doing that for arrangements of atoms. Okay? So when we talk about a lattice like this, a lattice is an array of points. It doesn't exist. It's in our minds. Okay? We are not yet putting any atoms on this, but this is a two-dimensional lattice. It's a square lattice. We have a set of points here, and we've drawn lines between the points. I could have chosen a different shape here to represent the same set of points. For example, if I draw this array of points, I could choose an oblique cell to represent the same square array of points. Yeah. And there are reasons for doing that. But the main point I want to make is that we simply choose a square cell because it's convenient to us, that the edges are of the same length, the angles are 90 degrees, and it does reflect the symmetry of the pattern. But there might be circumstances, which we'll come to much later, where we want to choose a different unit cell to represent the same points, array of points. And each one of these points can be the origin of this cell. They are exactly equivalent points. Okay? That's the meaning of a lattice point, that the environment of this point will be exactly the same as the environment of this point if I draw many more cells around here. So these are the lattice parameters. There's an angle here which is 90 degrees, and this is a two-dimensional unit cell, square lattice. What does the P stand for? So I've said this is a square P lattice. Primitive. What does that mean? You're right? Sorry? Yeah, so you're right. You said one atom in the cell, but we haven't got to atoms yet. So it's one lattice point per cell. You can have more than one atom in the cell and it can still be primitive. Yeah, I'll show you later. But it means that you have just one lattice point per cell. But why are we saying one? Because we've got 4 over here. Why is there just one lattice point per cell? How can I say that's primitive? Any ideas? Exactly. Yeah. So if I draw some more unit cells, you will have this point being shared by 4 cells. So only a quarter of that belongs to this. Okay. So if I add quarter, 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 I get 1 per cell. These are some alternatives where we've changed the length of the edge so that we have rectangles. This is the primitive rectangular lattice, and this is a centered lattice, a unit cell. So we have a lattice point at half, half, in addition to a lattice point at 0, 0. Okay? So this, how many lattice points would this have per cell? 2. Okay, quarter, 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 quarter plus 1. So there's 2 there. And this is the hexagonal, the primitive hexagonal lattice. This is special in the sense that this angle here is 60 degrees and this one is 120 degrees. But I could actually generalize this and relax those angles from those values, in which case I could get something like this, and here the lattice parameter is also different. So this angle is now not necessarily 60 degrees. Okay? So that's an oblique P lattice. Now the interesting thing is these are the only possible patterns you can get in 2 dimensions. There are no more than 5. So if you were making wallpaper, yeah, you know what wallpaper is, right? You don't use it very often in Korea, but in Europe, instead of painting, you put patterns of paper on the wall with flowers or whatever you like. And in principle, there are only 5 different kinds of wallpapers you can buy, because any other pattern that you draw will simply fall into one of these 5 arrangements. So how come you can buy many more than 5 different kinds of wallpapers? There is no other periodic pattern which will fit, which will create a pattern, a unit cell which is different from the 5 illustrated here. So why is it that we can buy hundreds of different kinds of wallpapers? The motif, the atom that we put at each lattice point can be different. It could be a flower or a bee or a cluster of flowers, etc. Okay? But the basic pattern will be one of 5 different kinds. Okay? Of course, you could have random as well, but a random pattern is very much more difficult to print when you are producing, lots and lots of wallpapers. So probably you would pay an enormous amount if you ask them to produce you a random wallpaper pattern. Now this is a carbon nanotube. Basically it's a sheet of graphene which has a hexagonal array of carbon atoms, and it's wrapped up into a tube, and there might be some objects, some closing of the ends as well. But you can get 2-dimensional crystals. Graphene, a single layer of graphene is like a 2-dimensional crystal. So this is our wallpaper, and it has a certain structure. There are these objects which are placed at each lattice point, and if you look carefully, you can see that is the unit cell. Okay? So the environment here is exactly the same as the environment here and here and here. Yeah, can you see that? Now if I repeat this, then I can generate, let me go back. I can generate the entire wallpaper. Right? Now, what kind of a cell is this? Is this a primitive cell or not? Yeah? You see that? Is the environment of this point exactly the same as the environment of this and this? Yeah? That means you have a lattice point here, and it's a centered rectangular cell. Okay? And if I repeat this cell, I can generate the whole pattern. How about these? Which of these patterns are unit cells? Is this a unit cell? Yeah, this illustrates the fact that we can have the same array of points represented by different unit cells. So previously we had a rectangular centered cell. This is now an oblique cell. But is that a unit cell? Can I put several of those and generate the whole pattern? Yeah. How about this one? No, because if I take another triangle here, then I'm left with a hole, right? So a unit cell must be able to fill the space. If you stack it and it doesn't fill the space, then it's not a unit cell. Similarly, this is not a unit cell. And you could argue that if I take one of these and one of these, then that fills space, but that's not the definition of a unit cell. You are using two different cells. There is a material like that, which has two different unit cells stacked together. About 2 years ago, there was a Nobel Prize given for a discovery which was made about 20 or 30 years ago. Quasicrystals, weird. So that involves, if you take one pattern and you stack it, it won't fill space. But if you take two different patterns, you can tessellate them to fill all space. Okay. And then you also get interesting properties which we'll come to later. So the definition of a unit cell is that it must be able to fill all space. And we need to go a little bit further. These cell edges not only have magnitudes, which we call the lattice parameters, but they also have directions. So effectively they are vectors. Okay? And this is A1 is called a basis vector, and A2 is also called a basis vector. And when we stack them together, we produce a repeating pattern. If we extend what we've done so far into 3 dimensions, we have exactly the same principles. We are still working with imaginary points, and therefore we can define cells which are different but represent the same set of lattice points. But we obviously have an additional axis, A1, A2, and A3. So 3 lattice parameters and 3 angles and 3 basis vectors. Okay? So the concepts are exactly the same as the 2-dimensional lattice, but we will have a greater possibility of the number of patterns. Instead of 5, we have 14 possible patterns in 3 dimensions. So just to summarize, each lattice point on your cell must have exactly the same environment around it. That's the fundamental definition of a lattice point. And that's why when you think about a dislocation which causes slip deformation, the Burger's vector must be a lattice vector. That means it starts at a lattice point and ends at a lattice point, because when you translate one half of the crystal relative to the other by a lattice vector, there's no change in structure, and slip doesn't cause a change in structure, right? Unit cell must fill space when you stack the cells, and you define the cell by the basis vectors A1, A2, and A3, which have magnitudes A1, A2, and A3, and the angles between the axes are labeled conventionally as alpha, beta, and gamma. And in 3 dimensions, there are 14 possible different unit cells. Okay, so we now come to how we index directions, planes, etc. Okay. Now, in the case of directions, let's say we are thinking about a vector u. We can write that vector as the sum of the weighted sum of the basis vectors, like u1, a1, plus u2, a2, plus u3, a3. So this forms our coordinate system, and you define the vector in terms of that coordinate system. And these components you write using square brackets, and those are the Miller indices of the direction. Okay? So Miller was a geologist in Cambridge University, actually, in the Earth Sciences department. The Miller indices are named after him. So here this vector u is obtained by translating 1 along here and 1 along here, and therefore the Miller indices are 1, 1. How about this one? Let's say it's going half along here. Okay, what would you label this as? The vector u? Yes, that's very good. So you already know crystallography, because if you had asked me, I would have said it's 1/2. Yeah? Because it's going 1 along here and half along here. So why have you chosen to call it 2, 1? Because we like integers, right? Yeah. So this vector is actually exactly 1.5, but its direction is parallel to 2, 1. So you label it as 2, 1. But if you want it to be accurate, say you were looking at the Burgers vector of a dislocation, then 2, 1 would not be correct. Yeah? You could write it in different ways. So it will be 1.5, okay, or that is parallel to 2, 1, but this is equivalent to a upon 2 into 2, 1, okay, assuming that it's a square lattice. Yeah. So it depends on what you're doing. If you're just referring to a general direction, then you call it 2, 1. But if you need to be careful about the magnitude of the vector, then you can write it like this and still maintain the integers inside the square brackets. Okay, so I'm specifically using square brackets for directions. Okay? Everyone happy with that? How about this? What would you call this direction? What are the Miller indices of this direction? Yeah? -1, 1, -1 and 1. And instead of writing -1, 1, you write bar 1, 1. Okay? And the second one, what are the Miller indices? Two, 1. So this genuinely is going 2 along A1 and 1 along A2. Okay? So directions are fairly easy to index. And in 3 dimensions, what would you call this vector? 1, 1, 1. And this one? Yeah, because it doesn't have any component along A1. So that's 0, 1, and 1. Okay, now we have a small problem which comes from symmetry. So assume that this is a primitive cubic unit cell. Okay, that means all the edges are of equal length and all the angles alpha, beta, and gamma are at 90 degrees. Then this direction is 1, 0, 0, because you're going 1 along A1 and 0 along that and that. But I could have chosen my origin differently and called this the x-axis, in which case this would be 1, 0, 0, or this one. Okay? So the arrangement of atoms along this direction is exactly the same as along this direction or this direction. And whether we call that 1, 0, 0 or 0, 0, 1 depends on our choice of axes, right? So it's arbitrary. So all of these directions are said to be crystallographically equivalent. Properties along those directions are precisely identical. And what you index them as depends on your choice of origin. Okay? So in order to identify crystallographically equivalent directions, instead of writing 6 of these, you use brackets like this, the braces. Okay? So that tells me that you're referring to a direction which could be parallel to 1, 0, 0, 0, 1, 0, 0, 0, 1, bar 1, 0, 0, and so on. Yeah. Okay, we now come to planes. In order to find the indices of a plane, we have here our plane, and it intersects here A1 at 1 intersects A2 at 1 and intersects A3 at a half, right? We then take the reciprocal of those intercepts, and that gives us the Miller indices of that plane, and we use round brackets for those Miller indices. Now, why do we do this? We will learn that more clearly when we come to the reciprocal lattice, okay, which is a few lectures away. But basically, the directions are vectors in real space. Yeah, so you just add up the components along the basis vectors and you get the indices of a direction. Plane normals, which is how you define a plane, are vectors in reciprocal space. And that is why their indices are defined by taking intercepts and then the reciprocals of those intercepts. So we'll come to that later on in the course. And we use round brackets for specific planes. Okay. Everyone happy with that? What are the indices of this plane? 1, 1, 1. Very good. Okay, so the intercepts along these axes are 1, 1, 1, and therefore the reciprocal of that is also 1, 1, 1, and we use square brackets to identify that specific plane. How about this one? Sorry? 0, 1, 0. What are the intercepts? Yeah, infinity, 1, infinity, and if you take the reciprocal of that, it's 0, 1, 0. There. Okay? Right, this one. 0, 1, 1, that's right. Okay. Right, and then we have the same problem that if our material is cubic, we have 4 of these closed back planes and their negatives. So there's a multiplicity of 8. And we really want to refer to just a closed back plane and say the indices, we are referring to the set of closed back planes which are crystallographically equivalent by using these curly brackets. Right? So square brackets refer to a specific plane, and curly brackets like this refer to crystallographically equivalent set of planes. Okay, now, I said to you that this course will deal completely generally with crystals, not just metals. We might deal with a crystal which has 56 atoms. Yeah, so do you know an example of a crystal with a large number of atoms inside the unit cell? It actually happens in steels. Cementite, yeah? 56 atoms in the cell. So, although it's very easy to draw this diagram here, which is body-centered cubic, it's no longer easy when you have a very complicated crystal structure. So my recommendation is you don't draw three-dimensional diagrams. They're not terribly useful as soon as you get away from the simplest of structures, because you need to rotate, look along different directions, and even then it can be confusing because of overlap. Yeah? This is called a structure projection. We are projecting along the z-axis here, and this lattice point is located at a height half, 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 right? We don't put the x and y coordinates because they are already apparent on the diagram, but we put the z coordinate. And when we don't put coordinates, that means there is a lattice point at 0 and at 1. Okay, so 0 and 1. Okay. So this is called a structure projection, and it's much, much easier to visualize than looking at something which is three-dimensional. So this is now a little bit more complicated. This is the face-centered cubic unit cell, where we have a lattice point at each corner and a lattice point at the center of each face. On the structure projection, it becomes very simple to look at. These are all at heights 0 and 1. So this is the face centering lattice point on the face parallel to the bottom. Okay, you can see 0 and 1. These are located at coordinates half and half upwards. For example, this point here. And these are the face centers of the vertical faces, basically. So this is the structure projection of the face-centered cubic cell. We also have a primitive cubic cell. Okay? And there are very, very... in fact, I know of only one metallic material which has the primitive cubic cell. It's polonium. Okay? Oh, it's not really a very stable structure otherwise. So most metals are either body-centered cubic, face-centered cubic, hexagonal, okay? And then you might get some with much lower symmetry. So these are the structure projections of the primitive, the body-centered, and the face-centered cell. So just as for primitive we write the symbol P, for body-centered we have the symbol I, because it's a German word for body-centered which begins with I. Okay? And F is for face-centered cubic cell. So there are three varieties of unit cells for the cubic class of crystals. We also need to think about symmetry. We've already talked about that by identifying crystallographically equivalent planes and crystallographic equivalent directions. So in the cubic system, we had 6 cell edges, which all have exactly the same properties. If I change that to tetragonal, then the A-axes are identical in the basal plane, but the C-axis is different. So the symmetry changes, and now I have 4 equivalent 1, 0, 0 directions, not 6. Okay? And so on. This is a mirror plane. So if I put an object like this, I will see another object at that location. This is a 4-fold rotation axis. That means if I rotate by 90 degrees, then I will find an object like this at that location, and here and here. So a 4-fold rotation axis is called the tetrad. I will come to that in more detail later. And of course, the very definition of a crystal requires translational symmetry, because the environment at every lattice point is exactly identical. Okay, so you can put your origin at any lattice point. So these are the basic elements of symmetry: rotation axes, mirror planes, and translational symmetry. There is another aspect which is a little bit more difficult to visualize. We will look at a 2-dimensional visualization of this when we do stereograms. But basically what it means is that if I take this point and I invert it through the center, I find another equivalent point on the other side. Okay? So there is an inversion symmetry in this. Now, why is this important? If you don't have inversion symmetry, then the crystal acquires properties which are unusual. So if I stress the crystal, then I might displace charges in an unequal way, and therefore I will get the crystal charging up, and you might get a spark. Yeah? So that's ferroelectricity. So your lighters. In the old days, the lighters had a flint stone, which is a stone which you which you strike and you get a spark. But nowadays it has a piezoelectric crystal, which when you hit will produce a spark. And that's the same in gas cookers. Yeah? You hear the click, click, click sound, that sparks coming out when you strike a piezoelectric crystal. So those will not have this center of symmetry. Okay? Okay. When crystallography first started, it was by looking at the beautiful shapes of crystals which you find in nature. Those crystals have had thousands and thousands of years to grow, and therefore they are close to the equilibrium shape of crystals. So just by looking at the symmetry of that shape, you could tell whether it's cubic or whether it's tetragonal or monoclinic or triclinic or whatever. That's how crystallography happened until diffraction and the Bragg law were discovered or invented around the early part of the 20th century. Before then, crystallography was by measuring the angles between faces of crystals. Very careful work. Yeah? Now, when you do that, when you measure macroscopic properties, you cannot, of course, make comments about the details of very small translations inside the crystal. Okay? So, for example, this is called a glide plane. This is a mirror plane. If I take this object and I reflect it, then I get this object here. Okay? So, if I have these two objects in my crystal, I know there's a mirror plane here. Yeah? There is another kind of a plane, which is called a glide plane. So, if I take this and I reflect it along here and then translate it by a fraction of a lattice parameter, say half a lattice parameter, then I recover this object here. There's nothing left here. So this is a reflection plus a translation by a fraction of the lattice parameter. That's called a glide plane. Now, when you look at the macroscopic shape, this appears like a mirror plane, simply because you can't pick up that half a cell edge translation. Okay? But when you look at the details of the structure, you find the glide plane. Okay? But you need resolution on the atomic level. This is like a rotation axis, but in addition to rotation, there's a translation. So exactly like a screw. Yeah, when you turn the screw, it also moves, doesn't it? So here, this is a diode. That means 180-degree rotation. If I rotate it along here by 180 degrees, I have a shape like this, and translate it by a fraction of the repeat distance, and I recover this. Okay? So this is a screw axis. And when you look at the macroscopic shape of the crystal, that will appear just like a rotation axis. You don't pick up that very, very small translation. Oh, yeah? A screw and a glide? Yeah. So in this case, let's look at the screw first. So this is the screw axis, and this is the repeat distance. Okay? That means this is, I could start here or I could start here. Okay? Now, when I rotate by 180 degrees, it produces this. Yeah? And if I translate by half of the repeat distance, then it produces this. So this is an axis of rotation, right? It's a line. Okay. Now, a glide plane is a plane. And I should really draw it as something like this. It's a bit tricky to draw, okay? But I'll draw black on this side of the plane and red on that side of the plane, right? So if I have this object here, then after reflecting, it becomes that object, which is on the other side of the plane. And then I translate by a fraction. Yeah. So just reflection would make this plane a mirror. So a plane, a plane might have other objects here, which have to behave in the same way. Okay? Yeah, exactly. So a plane is two-dimensional, whereas an axis is one. The axis itself is, one-dimensional. Okay. Right. So we have, we can define all crystals into 7 different classes, right? And within each class I have, for example, in the cubic I have primitive, body-centered cubic and face-centered cubic. So if I add up all the different varieties in these 7 crystal classes, I get the 14 different unit cells possible in 3 dimensions. Okay? And the cell is defined by the basis vectors. In the case of cubic, they are all identical in magnitude, and the angles are all 90 degrees. This is quite important, right? So if something, a triad is a rotation of 180 degrees, a rotation axis with 120 degrees. If you cannot find 4 such axes, it cannot be cubic, right? So do you know which direction the triad lies along in a cube? So along the body diagonal, right? And there are 4 body diagonals, which are the 4 triads. If you do not have 4 triads, it cannot be cubic. So we call this the defining symmetry of the cubic class of crystals. If I can only find 1 triad, that cannot be cubic. Okay? That is in fact a trigonal crystal system. In order to have a hexagonal system, hexagonal unit cell, I must have 1 hexad, with a rotation of 60 degrees, reproducing everything. Yeah? So when you look at the shape of a large crystal, and you can see along the body diagonals of that crystal and see that there are 4 triads, you know that it's cubic. You don't have to do any diffraction experiment. And similarly, if you can find a hexad, then it has to be in the hexagonal class. It cannot be in any of the others, because none of the others have a 6-fold rotation axis. So just by looking, all these crystal classes were derived not by diffraction, but by looking at the shapes of macroscopic crystals. Just came back last week from Russia, where I was visiting a minerals university, and I took hundreds of photographs of minerals which are on my website. And you can see the shapes of these very large crystals which have grown in nature over very long periods of time. Just by looking at those, the crystallographers derived the 14 Bravais lattices and the crystal classes and so on, with no reference to diffraction theory. Okay? Okay, so these are our 14 crystal classes. We have cubic P, F, and I. Then we have lower symmetries, and you've got the orthorhombic system where the 3 edges are all different in length, but the angles are all 90 degrees. And the lowest symmetry is the triclinic cell, okay, where none of the edges are equal and none of the angles are equal either. And this is a much simpler way of looking at those 14 as structure projections rather than the 3-dimensional cells. Is everyone happy with that? Okay, so I've taught you enough for you to complete quiz 1. Okay? And please do that, because you will be able to see what you don't understand. Because, sitting in a lecture, I'm telling you what is right and what is wrong, but you cannot test yourself until you actually try the quiz. Okay? So the purpose of the quiz is not simply to give you a mark at the end of the course, but so that you follow the lectures as we progress. And the second lecture then is not more difficult than the first lecture. Okay? Okay, so we will stop here today and see you tomorrow.